Hello. Today I'll be talking about some recent work on costly zero-order oracles. This is joint work with Renato, Paes, Leme at Google Research New York. So in this paper we study the following problem. You have a set S of points in d-dimensional Euclidean space. Your goal is to learn an unknown linear function f of x from the space to R. And for any x in the set of points, you can pay c of epsilon to learn the value of f of x to within epsilon. And the question is, how much do you need to pay in total to learn f of x pointwise over all the points in S to within epsilon? So in particular, you want to output a function g of x such that g of x agrees with f of x within epsilon for all points x in S. Great. So a quick note on some motivations for this problem. This sort of thing occurs pretty naturally in a variety of online learning and active learning settings. So some natural examples for C of epsilon, which arise in practice. If you have stochastic feedback about the value of f of x, your cost to measure it within epsilon might be something like 1 over epsilon squared. That's the number of stochastic queries you need. If you have threshold queries, like if you can ask, is f of x bigger than y or less than y for a y of your choosing, you need log of 1 over epsilon to specify the value of f of x within epsilon. And if you have threshold queries but non-adaptive threshold queries, you need to specify the values. You specify all your threshold queries in advance. This corresponds to a cost function of something like O of 1 over epsilon. And importantly, threshold queries arise naturally in pricing applications, which was the motivation for this work, where the idea is there's an item, it has some features. Based on these features, you can set a price for the item, and then you can see if a buyer buys it. And in the operations research literature, this sort of model is known as contextual pricing. Great. So if you're paying attention 2 slides ago, you might have noticed that the problem we stated might have a sort of simple solution. And like the most natural approach to this problem is sort of, since f of x is linear, it's specified by its value on d linearly independent vectors. So what you can do is you can just choose d independent vectors in S, measure each of them to within some precision, maybe O of epsilon over d, and then write each other point x in your set as a linear combination of your existing vectors, and then use this to estimate f of x. And this leads to a total cost of something like O of d times c of epsilon over d. And this is great, but it has a caveat. And the caveat is that this constant in the big O really depends on the set S of points. And in particular, it depends on the set of vectors you choose to approximate all the other points. So in particular, the precision necessary depends on how well conditioned our initial choice of vectors are. So in the previous slide, if we choose these 2 vectors, maybe we can get away with epsilon over d with a reasonable constant. If we choose these 2 vectors, we'll need a much larger constant because this set of vectors is a lot less well conditioned. And a natural question here is, what cost can we guarantee independent of the set S? Can we still guarantee the same total cost O of d times c of epsilon over d with a constant independent of the original set of points S? And the main result of this paper is that, in fact, you can do this. So what we show is that for any set S of points in RD, non-sterilely convex, and cost function c of epsilon, it is possible to efficiently learn an unknown linear function over S while incurring total cost at most O of d times c of epsilon over d. And there is a lower bound, a simple information theoretic lower bound of omega of d times c of epsilon. So in particular, this is nearly tight for threshold queries where c of epsilon is equal to log 1 over epsilon up to an additive log d-ish factor. Earlier I said efficiently, what we mean by this is with access to an oracle that can optimize linear functions over S. This is a fairly weak constraint. It's true for, or it's a general assumption for convex sets. It's true for point sets, and it's also true for weirder non-convex sets you can imagine, like unions of a small number of convex sets. So as a warm-up, let's consider what happens if S is convex. So the issue with the original idea was that if you choose a set of vectors which is ill-conditioned, you might have to pay a big constant in big O. So one thing you might want to do is you want to find like a representative orthogonal basis for S. And one great way of doing this is to use John's theorem. So John's theorem says that for any convex set S, there exists an ellipsoid E such that E is contained inside S, Importantly, S is contained inside D times E, the dilation of E by a factor of D. So this leads to the following sort of simple approach. What you can do is you can look at John's ellipsoid, and what you can do is you can query both the center and the principal axes of John's ellipsoid. And importantly, this lets you write every point in your set S as a linear combination of first C plus some combination AI times VI, where VI are these principal axes. And by John's theorem, since S is contained in D times E, we know that all of these coefficients AI are most D in magnitude. And in particular, this implies that it suffices to measure all of them to within precision and most epsilon over D squared. It's over D squared because you want to measure, if you measure them to epsilon over D squared, you measure each of the AI times VI's to within epsilon over D, because each of the I's is in most D in magnitude, and when you add them all up, you have error in most epsilon. Now, this is not the O of D times C of epsilon over D we said earlier. You can improve this slightly to O of D times C of epsilon over D to the 3/2, but also this method only works for convex sets S. So if you have a non-convex set S, what can you do? So one thing you can try to do is to perform the same sort of John ellipsoid trick, and take like the John ellipsoid of the convex hull, for example, but you might not be able to directly query the principal axes of this ellipsoid because they might no longer belong in S. So one idea is to, instead of doing John's theorem with an ellipsoid, find another polytope P with vertices in S, such that P is contained in S, because its vertices are in S, but such that S is contained within a small dilation of P, alpha times P. And in particular, if P has V vertices, then it suffices via Carathéodory's theorem to measure all of the vertices, f of all of the vertices, to within precision O of epsilon over alpha, for a total cost of O of V times C of epsilon over alpha. Great. And what we do is we show that we can, in fact, do this. So the main technical theorem in our paper is the sort of analog of John's theorem for simplices, in fact. So what we show is that given a set S of points in Rd, it is possible to efficiently find a simplex T whose vertices belong to S, such that S is contained in some translate of negative O of D times T dilated by a factor of O of D and reflected. So for in 2 dimensions, this corresponds to the problem like finding a triangle with points in your set S, such that a dilation of about a factor of O of 2 contains all the points in your set S. And by the argument on the previous slide, this theorem immediately leads to an algorithm with total cost O of D times C of epsilon over D, our main result. So this theorem has a very nice proof and simple proof, so I'll sketch most of the proof in the next few slides. So this proof is based around the idea of the outer dual of a simplex. So the idea is that you have a simplex T, it has D plus 1 vertices, V1, V2 through Vd plus 1. And from the simplex, you could construct a new simplex in the following manner. What you do is for every point V in your simplex, draw a hyperplane through this point, parallel to the hyperplane through the D other points, so through V2 and V3 here, and do this D plus 1 times for every vertex in your set. And these D plus 1 hyperplanes form a new simplex, and in fact, this new simplex is similar to the original simplex. It's in fact a translate of negative D times the original simplex. So how does this help us? So here's the main claim. Let's let T be the maximum volume simplex with vertices in S. Then S is contained in the outer dual of T. And there's a quick proof by picture here. This is, imagine this simplex here is the maximal volume simplex. This blue simplex is its outer dual. And assume there's a point in S which is not contained in the outer dual of T. That means that if you take the simplex containing V2, V3, and X in this case, it will have higher volume than the original simplex you started with, the supposedly maximal volume simplex. And in particular, this generalizes D dimensions. Just if you have a point X and S which violates one of the hyperplanes, that point, along with the D other points, is a larger volume simplex than your existing volume simplex. Great. So this actually proves the theorem if you're not worried about doing it efficiently. But there's an important question, which is, can you find the maximum volume simplex efficiently? And this is a well-studied problem, and it's known to be computationally hard. And there's not even any known sub-exponential approximations. The best sort of approximations are finding simplex with volume 1/2 to the d times that of the maximum volume simplex. So it is possible to get around this. What you can do is you can work with a local approximate variant of this maximum volume simplex. So in particular, we say we define an alpha maximal simplex. We call a simplex alpha maximal if you cannot increase its volume by more than a factor of alpha by changing at most one vertex. And one claim, which we won't prove here, but we've shown in the paper, is that given any constant alpha bigger than 1, it's possible to find an alpha maximal simplex in polynomial time. And it turns out that these previous claims we made about the maximum volume simplex, that it's contained, that S is contained without a dual, is almost true for an alpha maximal simplex. Great. So I'll conclude with some quick open questions. So I mentioned that in this paper we show this O of d times C of epsilon over d upper bound. The best lower bound we have from the simple information theoretic argument is omega of d times C of epsilon, and it's interesting to figure out what the actual answer is. So it's possible some volume arguments that suggest that the current approach of like picking a polytope and containing S in the dilation of this polytope can't beat O of d times C of epsilon over square root of d. And we think that this might be the correct answer. We think that this might be tight. The second sort of direction that might be interesting is the power of adaptivity. All of the algorithms we propose so far are non-adaptive. You can specify all the queries and precisions in advance. Is it possible to gain any power by being adaptive? And we don't know any algorithms which gain anything by being adaptive right now. And finally, one last interesting open question, which doesn't help learn linear functions any better, but sort of interesting in its own right. In our John's theorem for simplices, we find a simplex t such that S is contained in a translate of negative t times t. But you can ask the same question of what's the best dilation factor you can achieve if you insist that the dilation factor is positive? What is the smallest beta bigger than 1 such that there exists a simplex t with vertices in S such that S is contained in beta times t? And we conjecture that beta equals d is possible, but the best we know is beta equals d squared. You can get this by just applying this sort of theorem twice. And even in 2D, we don't know the answer. So this is a interesting question we don't know the answer to, which is, if you have a set S of points in 2 dimensions, can you find a triangle T such that the entire set S of points is contained inside a translate of 2 times t dilated by a factor of 2? I'm happy to talk about this if you have any ideas. And thanks for listening.